We are good to go. So I'm going to go ahead and begin. I'm Stephanie. I'm the instructor who will be listening to today. And today's program is about using PyTorch with Dask. So parallelizing and scaling up PyTorch processes with Dask. And so what we'll be talking most about is how Dask can really enhance the PyTorch existing toolkit. Because as you're probably aware, if you're familiar with the Saturn Cloud product, we intend to provide augmentation to the existing PyData toolkit to make it more scalable and more parallelizable. We'll talk a little bit about that in a minute. I'm, as I said, a senior data scientist here, and I have a colleague who will be joining us also as our sort of second in command help and support team. And so, Aaron, you want to introduce yourself?
Yeah, sure. Hi, I'm Aaron here, also senior data scientist. I'll be on here. I'm also monitoring the Slack channel. So any technical difficulties and anything, I'll be more kind of behind the scenes. If you have any questions, I'll be answering you there. So excited for the workshop.
Awesome. Thank you. Okay, so as I said, Slack is for conversation, chatter, any questions that you have. However, during this workshop, I'm also going to, add a few points to make sure that everyone's following and everything is making sense, and that I don't need to pause and wait for people to get caught up. I'm going to use the reactions, which are a part of the Zoom interface. So what you'll see at the bottom of your screen when you're looking at the Zoom window is a little button that says reactions, and there'll be a selection of little emojis you can use. So from time to time, what I'm going to do is I'm going to say, if you're ready to move on, or if you've got it all figured out and you're done with that section, hit me with a reaction, and you can pick whatever emoji makes you happy to use, and I'll be checking everyone's screens to make sure that we're all on the same page. So just make sure that you know where that is, and that when I yell out that we are doing that you can find one. In addition, some of you all today are participating by working through the actual notebooks in the Saturn environment, and some of you are just going to be observing and reading the notebooks that have been pre-run. So if you're going to be participating, you want to make sure that your Saturn environment is already spun up. If you're using Saturn hosted, you'll see the link on the screen that is the community Saturn product. If you're an enterprise user, then you have your own Saturn installation, and you probably know your URL, but it's going to be in that same sort of format as you can see on screen. In the case of those who are participating in the Saturn environment, you already have an account set up, you already have the project and the resources that we are going to be using already set up. So all you need to do is hit the little green arrow buttons on those things to spin up those and allocate the resources to those, and then you'll be all set to go. If you're not going to be participating, you're just going to be watching, you can just follow along directly on GitHub. You can just read the notebooks there. There's a notebook output folder that has notebooks fully run with everything completed. I would recommend, if you don't mind, cloning the repo down to your local environment, just because the notebook's going to look a little nicer on the local environment. The GitHub renderer for Jupyter notebooks is not bad, but it could be better. But otherwise, that's all you should need, and we'll be everyone will be working on or following along on the same material, so you shouldn't have any confusion or challenges in terms of keeping up. To then just sort of get us started, what I'm going to talk a little bit about in the beginning here, before we get into the notebooks, is kind of what it is we're here for, and what the purpose of the Saturn, interface and the Dask toolkit really is. So we start from the sort of comfortable place that a lot of us are very familiar with and have a lot of experience with, which is doing machine learning in the broader PyData Python stack. There's a lot of tools that are incredibly popular and incredibly vital to our everyday effectiveness and the work we do. And they work really well, and that's one of the reasons that they're so popular. These are things that we are very the APIs, the framework, and the concepts around how we think about the code that we're writing and the analysis we're doing are kind of shaped by these tools. So when we get to the point where we may need to scale up, which could either be because we are compute bound, needing to add more actual processing resources in order to complete the tasks that we want to complete in time that's reasonable. Or we're memory bound, where we have such a large volume of data, an increasing problem in this day and age, that we need to have more ability to handle that, whether that's just adding more memory or adding some other kind of alternative process, downsampling, that kind of thing. Then we need to start thinking about how do we, using this baseline Python stack that we're so familiar with and that we're so happy with already, how do we make that better? How do we bring that to another level? And so Dask. Dask is this distributed computing open source framework that takes these tasks that we're building in Python, lets us stay with the same Python APIs and the frameworks and the concepts that we're used to, but takes these tasks and lazily evaluates them. And we'll talk a little bit later about more what that means. But it takes these tasks and allows you to pass them to a cluster of workers and then have them be run in the most efficient way possible with the most parallelization possible, so that you can make a lot more get done in a lot less time. We also have a framework inside the Dask ecosystem called the Dask data frame, which allows you to have distributed data storage on your Dask cluster, still staying in the sort of Pandas API and Pandas thought processes that you might already have for the data that you're currently using. And all of this is possible without having to, massively increase the size of your single machine, because you're able to spin up a cluster on demand and then reduce that back down when it's no longer needed. This is the kind of what they call bursty work in machine learning that really can be a cost center if you're not able to add resources when you need them and reduce them when you're not in need of them. So that's what we're going to be talking about. We're going to say we've got PyTorch workflows that are awesome, but we need to either get them done a lot faster, we need to use a lot more data for them, or we need to make them a lot larger in terms of the computational sort of weight, and then we'll apply Dask to make that possible. So Dask is based on this idea of using workers clusters in order to distribute out that work to multiple machines. And there are lots of ways that you can do this. You don't need, theoretically, a product like Saturn to do this. You can spin up your own Dask clusters and you can manage all of that directly with, say, AWS or whatever resource provider you want to use. And you can just do all of this by hand. However, that takes a lot of time and a lot of specialized knowledge, and you may have to learn a whole heck of a lot that you might not have time for. You might have a lot of other things that you already need to do. So that's why the Saturn Cloud platform really exists, is to give you access to all of these amazing resources that the Dask framework allows, but you don't have to deal with spinning up the Kubernetes resources and dealing with whether machines are up or down, or dealing directly with all of the AWS resources that are complicated and difficult to sort of manage, when all you really want to be doing is running the machine learning workflow that's going to help your business get to the goals that you've set out. So we have the platform, which you're going to see today. We have the hosted environment, which is sort of for 1 or 2 user sort of situations, or the enterprise environment, which is for larger businesses that want to use your AWS account and have that extra level of sort of control and security. And we have folks in our community Slack, of course, who would be happy to talk to you more about exactly how that all works. But with that, you kind of have the general gist of what it is we're here for. So we're going to go straight into the notebooks at this point. Once again, you got these links, got the GitHub, and as I said, if you have problems or if you have issues, please visit us on the Slack channel. Or if if you don't think you have time to go through all of the rigmarole of getting in there, just open up the GitHub link and you should be all set. So now what you should be seeing is the Saturn Cloud product interface with the workshop Dask PyTorch page showing. And this is basically what your project should look like if you're logged into the Saturn Cloud environment now. If you're not, feel free to just watch along and see what I'm showing you here. But I want to give you a little bit of a walkthrough of exactly how the platform works before we get too deep into the weeds. As these projects are set up, you have potentially multiple projects that you can create here. Each one of those will have some resources attached, which we'll show off in a minute in the first notebook. And so when you get into your project, you've got your Jupyter server and an optional cluster. If you're not going to be using parallelization or using anything high, complexity for your project, there's no need to spin up a cluster if you don't want one. And then you'll hit Jupyter Lab here or Jupyter Notebook, depending on the way you like to work. And then you'll end up in something that looks like this. And this page is exactly what your notebook should look, your working environment should look like right now. We have a couple of folders. This is exactly the replica of the GitHub repo. So if anybody's on GitHub, you should be able to see these same things. If you visit this notebook output folder, you'll see all of these are exactly the same names as the notebooks in the main repo. And that's because these are the same notebooks, just fully run, all the results already printed out, so that you don't have to be able to print to run the work on the cluster in order to see the results. But what we're going to do is we're going to start with notebook number 1 here. Open that up. And then what we're going to do is beginning, we're going to talk a little bit about Dask and how Dask works a little more in detail than I've talked about previously. And we're going to talk about some of the concepts in Dask that you'll need to know in order for the rest of today's workshop to make sense. And then I'm going to give you a few sections of it. From time to time, there will be code that you'll need to read and fill in some blanks. And so in the end of this notebook, it'll show you exactly sort of what to expect from that. But first, talking about the Saturn Cloud concepts, we've already talked about the project. And one of the things that we don't see in the one that you're seeing here today, but that you should be aware of, is the concept of a deployment resource on a project, which would mean something like an always-on dashboard, for example, or something that needs to be serving, sort of some function without being associated with a Jupyter notebook. And so you can create those as well, and then have the optional Dask cluster associated with that if it's needed, or not if it's not. Images are Docker images, and that should be pretty, I think, straightforward for a lot of folks who are familiar with the idea of just creating an image that will give you the environment packages and libraries and dependencies that you will need for your work. We have some default images that are available for all users for Saturn Cloud. The one you're going to be using today is our default GPU image with just a couple of libraries attached. You'll notice if we go back here and look that we've got a start script that adds a couple of little libraries, 2 of which are for visualization, and 1 of which is the new Dask PyTorch DDP library, which we'll learn about a little later, that Saturn Cloud has recently developed and made public. And you can add any other little libraries that you need here, but by and large, we're just going to be using this base GPU resource utilization image, and it does all of the things we need it to do. Jupyter Server Dask cluster deployment should, I think, pretty much speak for themselves. And then you'll notice that the file system is based on these persistent volumes, EBS volumes. So if we were to shut down this Jupyter environment and then bring it back up later, all of our files will still be there. And that's a really handy thing, so that you're not starting from a total tabula rasa every time you start this up. So now there's going to be a couple of sections here that I want you all to take a look at and look through how this the Dask cluster running starts, and checking to see whether you have GPU available on your particular environment. So for those of you who are just following along, you can go ahead and just read through this section. And for anybody else, you'll have a little bit of code to actually run down here. So I want you to go ahead and do that. I'm going to put a timer up on screen here in just a moment. So we'll give it, say, 2 minutes for everyone to read through that, follow along. And then once you're all the way down at the end and little pup has run into your face, then give me an emoji on the screen. Remember, a reaction, so that I know that we're ready and that we can all move on. Okay. All right. I think that looked pretty good. So let's move along. And if anyone has questions or needs any additional help, once again, remember our Slack is there for any support. Okay, so now we're done with notebook number 1. And what you've gotten to see is the sort of how we're doing this fill in the blank section. It's just a little bit more interactive piece that you can use to check your understanding, make sure that things are making sense as we move along. And if you find that there's an element that really doesn't make sense, or you're just completely lost, you can either check the Slack for support, or you can also just click this little ellipsis here and it will pop open the answer to whatever the chunk right above it is. So you can just check that to check your understanding, or to, you know, just get it out of the way so that we can move on to the next section. Okay. So we can go ahead and click on the notebook number 2 link. And now we're going to get into a conversation a little bit about Dask and some of the essential concepts that you need to know. The thing that we're going to do here is we're going to apply a couple of different frameworks from Dask, sort of the different methods for parallelizing tasks, because there are a lot of different ways to get the same or an essentially similar result with Dask. You don't have to follow one singular method of getting things accomplished. But as we've talked about already, the concept is that you'll probably need to apply Dask either when you're memory constrained, loading and handling very, very large data sets, or when you're compute constrained, whereas many tasks need to be done at once, or many very complicated tasks need to be done. Delaying is the concept of setting up a function to be lazily evaluated. And so when we're talking about delaying a task with Dask, we're going to, instead of going straight from call a function is evaluated immediately, which is, you know, what you would see in normal Python code in the day-to-day, what you'll do is you'll create a function, call a function, but it will be held sort of in stasis until you indicate that you want computation to actually proceed. So you call a function, and you have an object that is function waiting to be run, and it's there, it's waiting for you. And then when you call compute method or persist method on it, we'll talk about in a minute exactly what the difference is, then you get computation proceeding, and then you get results, which means that once that function exists, but it's delayed, that's the perfect time to, say, distribute it across your cluster, so that then work is being disseminated across the available resources and not all having to be run right at the moment in which you developed it. So there's a few different things about this that you may need to know. So there's obviously decorating a function, which is at dask.delayed, which is just something you would call directly from the Dask library, which means any code that you've already written, any function you've already developed, you just decorate it with at dask.delayed, and it's now a delayed function that can be distributed out to your workers in the way that we just talked about. But there's also a ton of functions that are already, you know, parts of NumPy, parts of Pandas, parts of scikit-learn that had just been ported to be native to Dask. And so there's a sort of parallel track of the same API, the same functions, generally the same concepts that are available in the Dask natively. So you don't have to create them, you don't have to decorate them. You just call the Dask libraries that are equivalent to the Pandas or scikit-learn libraries that you're used to, and they'll do the exact same thing that the sort of basic library would do, except they'll do it on a distributed basis, and they'll pass the work out to your workers without you having to do any of the managing of work distribution or anything like that. So regardless, though, you need to be able to decide when you want your code to actually run the computation. You need to decide when the calculations need to be completed, when the function needs to actually be run, and the results need to be returned. And so persist and compute are the two methods that you can use to actually do that. What is the difference between these two things? It's actually a lot simpler than you might think. The names don't vary. I mean, in my opinion, the names don't really clearly articulate what they actually do. But think about it like this. We have our workers in our cluster. We also have our Jupyter instance right here, and we're running most of our code right locally on our Jupyter instance right in front of us. When we use compute, we're saying, okay, run all the computations that we've already queued up that are on our delayed function, and then bring all of that to be housed in the memory of our Jupyter instance right here. I want it right here, available to me, not distributed, not on the cluster, but back to the home base. And so if your data is too large to be held in local Pandas memory, if your Jupyter instance is not large enough to hold the data that you've just calculated, explosions can occur, so to speak. However, if your data is relatively small, if you're returning just a single value, for example, or just a vector that's relatively small, no problem, that should work just fine. So what you're doing is go out there, do the work on the cluster, bring the results back, back to the Jupyter instance. Persist, on the other hand, is all of that up to the point of completing the work on your cluster, but then the end result is retained as a distributed object on your cluster instead of being brought back to Jupyter instance. You can still, run computations on that object, even though it's distributed. Of course, we've got that based on the Dask ecosystem, but that will allow you to continue working on data that's too big to be held in the memory of your existing Jupyter instance, which is one of the huge advantages of Dask. So if you want to, say, run the computations you've queued up all to this point, and then continue working on the object that you're dealing with, or the data frame you're dealing with, still distributed, then persist is probably the right choice. These are concepts that may take a little time to sort of wrap your head around, and that it makes a lot of sense. And that's one of the reasons that we're here to help and here to give advice or answer any questions that you might have. So we've gotten to a good step, right? We've got to the point where we have our opportunity to, say, use the delay decorator in a function. We'll queue up some work and it's ready to go. But now we need to actually say, okay, now put it on the workers to do. Don't just do it locally on the Jupyter instance, put it out there. And so the distributed module of the Dask library is what you'll need to be using. We make a connection to the client. You've just done that in notebook number 1. We're going to do it several more times, so you're going to get lots of practice. And so then we have the choices of either calling submit on that, or on that client, or calling map on that. Submit means we take one task, we send it to the cluster, we run it on the whatever worker is free, or we can specify exactly which worker we want it to be on. But it's one task run one time. And so if we use map, like you might think of with map in broad contexts of other Python programming and other programming languages generally, you're taking a lot of tasks and you're going to map them over, taking one function, you're going to map it over a lot of inputs. So we've got maybe a whole list of different numeric inputs that you want to pass to the same function. You want to create a whole lot of tasks, same function, different inputs. Map will create all of those and then distribute them to the workers in the most efficient way to be run without you having to handhold any of those steps. There's also a method called run, which is really you send one task, the same task, same inputs to every worker simultaneously. However, it is mostly just for small utility tasks. It's not really for used for doing larger computations or things like that, but it's there and worth knowing about. So we're going to use map in a lot of the different stuff that we do later on. We're also going to use submit for a few of these things because we're going to want to make sure that we assign a specific worker, which you'll see later in the section after the break. But there's also an element called gather that's important. So when we're using gather, if we've put out a task or set of tasks across our cluster, we need to tell the cluster that then we want to return all of those results at the end. So the .gather method will actually do that before we compute. So we'll say, hey, now worker, map our delayed function over this list of inputs, pass them out to the workers, bring them all back, but it's just going to wait. It's just going to sit there because it's like, okay, you've queued up all of these things. They're all delayed. They're lazily evaluated. I don't work until you say compute. And so once you say compute, then it will all start going. And so that's, I think, a helpful way to sort of think about these things. And we'll see it all in practice in real time in just a moment here. So that is our sort of once over of Dask and how all of that works. And then, yeah, now we're ready to move on to actually running some PyTorch stuff and seeing how it plays with the distributed toolkit. So we're going to move on to notebook number 3 now. So go ahead and pull that up when you're ready. And so here we are. What we're going to do with notebook number 3 is to just take a look at a basic single image inference task so that we can see where we're starting from. So this isn't going to be real complicated, and it's not going to, I don't think, stretch anybody too hard, because we're just going to take ResNet 50, we're going to pull that down, and we're going to connect to an anonymous S3 bucket, a public S3 bucket that we've made available that shows the data from the Stanford dogs data set, pictures of dogs of different breeds grouped together so that you can train that on identifying breeds of dogs in random images. So once we've run this first chunk, we have our S3 bucket, and we're connected to that. And we're using the S3FS library for S3 connections, just for your reference. And then we're going to use the companion library Torch Vision from PyTorch to get access to the ResNet model. And we'll just run this chunk right here. And with that, simply enough, we have now the ResNet model locally available to us. And we also pulled in the ImageNet-based label set, which is the label set that you want to use with ResNet of various sorts. So with that, now we're ready to actually run a training, an inference, pardon me. So we're going to use one particular dog image here that's in this public data set. This is just going to be our test case. We're going to run this particular one, and then we're going to apply these particular transformations to it. Nothing particularly out of left field here. So running that should take just a second. And this is a whole very sort of run-of-the-mill approach to doing a single image classification. But it's important, I think, to start with the basics before we add complexity, and the complexity that includes parallelizing and doing this in a batch at a high volume scale level. So we've got a function that I've already written for you that will do the classification. So it's going to run the transform on your image, do the manipulations that need to be done on the tensors, and then return you the label that you're actually looking for, as well as a visualized, human readable image of the actual dog. So we're just going to run it right here. So you go ahead and hit this chunk. 182 milliseconds, easy peasy, super fast. That's wonderful. And now we've got our dog. Let's see what labels the model gave us. Looks standard, looks reasonable to me. This probably something in the Labrador range. So so that's the sort of starting point, right? So we pull our model, we get our image, we do a little bit of transformation to that image to make it computer readable, pass it through the model, get our results back, and then we adapt slightly the results from the model to be human readable once again. So what we're going to do now is we're going to think about, okay, well, the Stanford Dogs data set is over 20,000 images. And so we've got 182 milliseconds here. That's good. But once you start getting into like real volume of images, and if you say needed to classify 100,000 images a day for a production task in your workplace, this might not, doing these one at a time, especially the time spent loading the model and doing all of that, that's going to take longer than you have available for sure. And it's going to take a lot more resources than you might want to use. So what we're going to do is we're going to apply Dask to make this task a parallelized batch job so that we can identify all of those 20,000 plus images in the time it takes to just basically read one of these notebooks. So what we're going to do now is move on to notebook number 4, and you should have a link at the very bottom here that you can just click right in. And so we're going to scale it up. So you've already done the whole connect to the cluster thing once before, but just, let's run it again just to make sure that we all remember exactly how. We've got our cluster, we've got the IP addresses for those, and then we've also got this dashboard that we'll be able to use later. There's going to be a link at the bottom of the notebook as well, so you don't have to necessarily click through it right now. And then we're going to use this little chunk, which is just pulling the Python script that I've made in advance for you that's going to create some of the functions and load some of the libraries that we just used in Notebook 3. We're really doing the same task. We're taking the image, taking the model, we're running the inference, and we're returning the results. We're not going to return the picture itself because 20,000, but I want to emphasize that we really aren't refactoring very much at all of the underlying process. We are just adding some decorators of Dask delayed, and we're passing things out to the cluster and bringing them back. So go ahead and run this next chunk here.
Stephanie, when in the code that does Saturn cluster there, are we creating the cluster at that point, or was it already created and we're just connecting to it?
You're just connecting to an existing cluster. However, if you didn't already have one, this would create one for you. So this is more, if I was to just comment all of this out, it would just connect to the cluster that already exists. But what we wanted to do was to make sure that you could see the arguments that pass into this, so that if you were really like starting from 0, you wanted to programmatically create your cluster as well as going through all of the rest of the work, that you want to be able to see that you can do that here. If you run this and the cluster doesn't exist yet, instead of saying cluster is ready, it will give you a message about the cluster is pending, and it will check from moment to moment to check that it's pending. And then when it's ready, it will return cluster is ready and let you go on.
Thank you.
All right. So we've got our setup all done. We've got the stuff that we needed from notebook number 3. And of course, this is all in the GitHub repo. So if you want to see exactly what we're doing in the setup beforehand, feel free. And so now one of the things that we need to think about is how we assign objects to our GPU resources specifically here. Because we're working on a machine that has GPU available, but in the absence of any other instruction, our workers are going to try to run processes as CPU processes. So one of the things that we're going to do is we're going to take some PyTorch toolkit that already exists. It's not Dask at all. It's just a handy bit that is already part of the Torch library. And we're going to say, if CUDA is available, we're going to run it as a GPU, right? And then if it's not, we'll just go with CPU and that'll be fine. So here we are checking internally to see if we even have GPU resources available, and say, for whatever reason you didn't want to use a GPU, or if you didn't have one available, or any kind of consideration, you just easily keep running these things on CPU. It won't be as fast, and you'll be missing out on some of the parallelization sort of value add, but it's still probably be fine. And then we're going to do the same thing that we did earlier. We're going to get that ResNet 50 model, and then what we're going to do is we're going to say, okay, ResNet, now you're going to be running on GPU resources, because remember up here we just said it's going to be GPU stuff. So we're using the this little .2 call to instruct it that when we use this model, we're going to be using it on GPU compute resources. So go ahead and do the next chunk. This shouldn't take any time at all, but we've got this image underscore T object, which is the tensors of the single dog image that we used in Notebook 3, already exists. Go ahead and fill in how you would instruct to run computations that involve this image, or work involving this image on the GPU. And I'll just give it another, I don't know, minute, because I don't think this should take a whole long time for you guys. And then give me a thumbs up on your screen, or whatever reaction makes you happy when you're ready. Okay, go ahead and get back to it. And once again, you've got your little ellipsis here, so you can fill it in. It's just .2 for this as well. When it's an object that is a TensorFlow object, you can just use .2 to set it to the type of compute you want to use, and it's already ready for you to go ahead and use GPU for. So then we talked previously about the transformations we're going to apply to our image. It's really not anything complicated. We'll do a little resize, we'll do a little crop, and then we'll make it tensors. Easy enough. But we also, in this case, one of the things to note is that, and I think you've already seen this when you had the first notebook open, is that the image files that we're using from that public repo are actually contain the labels and the ground truth information, and also a unique identifier for each image in the file path. So I'm using a little regex magic that you don't need to worry at all about in order to extract the ground truth and the unique identifier for the image here. And so that's really all that this is involved. So this function of pre-processing the image, we have defined our transforms, we are opening the image and applying the transforms, and we're returning the unique identifier, the image transformed, so the tensor object, and then the ground truth. And that's that. And so we'll go ahead and run this. And you'll notice that I've applied that Dask.delayed decorator to it, right? And this is important to keep in mind, because it's still running. It's taking its sweet time. Importing Dask is probably the thing that's taking a minute. So what you're doing is just creating this function that you'll be able to use a little later.
It worked immediately on mine.
I don't know what mine is. Oh, there it goes. I must have just hit it at just the wrong moment. But okay, so you know what this function is doing. And this is, the sort of function you would use anytime you're building out a workflow for large scale image transformation or computer vision tasks at all, right? What we're going to do then is grab our images from the repo that we already talked about. So go ahead here. We've already got our S3 connection set up. And that should just take a sec, because it is going to have to get all of this 20,000 images and label and grab their file paths. So you'll see that takes a sec, and then we can see what we're dealing with, right? This should be familiar. We've got the ground truth, and then we've got the unique identifier for the label. So the label, the ground truth classes are the breed, right? And so that's this part, and then we've just got our unique identifier for each image after that. So this is the input that we're passing in, and then we can do this just like so, is a list comprehension, and it will run real quick. And there we are, batches of images. You'll notice that it was really fast. And this pre-processing would not be that fast, but it's delayed. It hasn't actually done anything yet. It's just sitting there waiting for us, because pre-processing is saying, okay, you've queued this up. You want to do this at some point, not right this minute. So fine, we'll set it up. We'll get all of the pointers where we want them, and we'll just wait for you to say go. So now we have a second function, which is taking the images that we've done one at a time and collapsing them into batches of 60, because we want to pass batches into our PyTorch process. And if you've done work with large volumes of data with PyTorch, you're probably familiar with this idea of creating these larger batches. And so that's all that this function is doing. It's probably not even really that necessary for a lot of the workflows that you might do. You could just incorporate this into a function prior to it. But one of the things to note is that in this, what we're passing in is the object we just created that doesn't exist yet. It does as pointers to instructions that are previously queued up, but it's just instructions. Like image batches, if we actually take a look at it, we go right here, it's not going to give us a list. It's going to give us a list of delayed tasks, right? So that's the thing to keep in mind when you're dealing with that. We're just giving it a bunch of delayed instructions, and it can then run some stuff on. So now we've got this reformat result for resultant image batches, and we're writing over the next one. So what we might want to do is take a look at actually what it is. 60 different images, they're all being transformed, and then they're all being smooshed into this one list. And that list will be our batch that will pass into our object. This is one batch at one time. We have several hundred batches because 20,000 images, batches of 60. So now we're really ready to just go ahead and run the inference. We've got the stuff that we've created up above. We have these batches of 60 images at a time, and they're all nicely organized into lists. You might be familiar with the concept that we need to stack the tensors. And this is an interesting piece. And this is why it's worth thinking about the objects that you're dealing with in this case, because what you've got are a list of references, but you can't stack just anything. You have to be tensors to stack them, right? So what we're actually going to do is inside our task, we are going to run the stack after we run the computations that get us to this point. So you'll see it in the bigger function that we do later on. But for now, let's just walk through an example of a single batch, just one chunk that maybe, all chihuahuas for all I know. And then we'll take a look at exactly how that works. And then you'll see it properly scaled up on the cluster, and we'll be able to watch the cluster run and watch the processes move on the GPU and the CPU as we go. So here's an example. If we run a single compute here, we're getting everything up to this current moment. All of this transform stuff and all of the list stuff and all of this, regex business, it's all being run right here. And so now we have iter item, I'm not good at naming things, sorry, that is the result of one of those. And it will be the names, the images, and the labels in a list of each one. So it's a list of names, a list of image tensors, and a list of the ground truths. And so here, we can go ahead and do that. And I didn't import Torch, did I? There we go. I always forget to import one thing or forget to run one chunk somewhere. So now we have a stack of tensors. Great, all set, ready to go. So we could do the next bit with like almost no work at all. ResNet, we've got it. ResNet put on the GPU compute, no problem. Set it to evaluation mode, naturally. With the images, this whole stack of tensors on our GPU compute, and then we run the model on the images. Now that, I didn't run the chunk that I told you so much about. I apologize. It's always something and I forget to run. There we go. So now we have our batch of predictions that are based on those images. And so I've got a little function here that I use to make those predictions more human readable. Because if you've ever gotten these directly out of the sort of horse's mouth, there's a lot of confusion there. And we're going to use these existing classes to match them up so that we know exactly what it's actually referring to. This stuff is just, processing of results of PyTorch classification. It shouldn't be anything particularly complicated, but if you have questions about this, please let us know. But we're going to go ahead and run that. It takes just a second. We've evaluated the predictions, got the true labels and the classes of the results. And so we'll go ahead and run this next section, which is evaluating the truth state, which I like to do just because I want it to tell me true or false at the end. I just like that because especially when you're dealing with the JSON like this, what we would normally do is spit all of this out into S3, just dump it all into S3 bucket, one per image, and then let that run so that then you can load all of that stuff back in from JSON really conveniently. I like to be able to do that because then you can just manipulate that data or get it back or analyze it the way you want to. But so we've got, this is the image, ground truth is Chihuahua, prediction is 93% Chihuahua, true, correct, yes. Good job. Okay. So all of those steps, this has just been run on a single batch of 60, and you can see that it's quite a bit faster. We're using the GPU, even though we're doing only one test, because we're running the inference on 60 images. So we can make it a lot, we can make a lot happen with this by now moving it over to run on all of the batches that we're dealing with. And so the next section you'll see there's a couple of fill in the blank pieces. And so all of this is exactly the same stuff as we created up above. So you should be able to just look above and then look down here and see, okay, what does this need to be? What does this need to be? You should be able to find all of these previously. And if you have any trouble, of course, there's the ellipsis down here below. Feel free to click that and to check your answers or to check and see if you're unsure about a thing. But this might take a couple of minutes, so I'm going to head and set the timer for, I think, 3 minutes and let everyone work on that for a moment. And if you're just following along, you can check those out or read ahead, and then we will move into actually running the whole job on the cluster. Next thing we're going to do is we're going to actually pull up the links to the cluster. And this stuff is a little bit of a cheat for me because I put the stuff in the setup script that will allow us to have these links. But so you can see the dashboard here is the CPU. And you'll see it's clean and ready for us to do stuff. And then there's GPU dashboards for both utilization and the memory. So we'll just pull up the one for utilization here. And so once we hit run on this next section, which is going to map our function across our image batches. Remember, we talked about how map works on the cluster, and then it will distribute those to the cluster in the most efficient way. And then we'll instruct it to gather back the futures that are completed when they're done. And then we hit compute so that all of those instructions are processed. And we have a little bit of error handling here just in case, because one of the things you might run into, it happens from time to time, is an image is malformed or a file is corrupted or things like that, especially with very large image sets. This is definitely a thing that can happen. So we've set this up as just a handy way to make sure that we're catching errors if they should occur. You shouldn't have any because we've made sure to test all of this a million times in advance. But for your reference, that's what that is. So we can go ahead and just run this chunk now. Go ahead and hit that, and it's going to sit and it's going to run for a little while. We're going to go ahead and take a break in this moment while we're waiting for that to run. But I just want you to see what it looks like when it's running on the CPU here. This is the part that's going to be running the image pre-processing tasks, which it takes a second to get itself moving along. But then this is going to be where you'll start to see GPU utilization, and since we have 3, it will start spiking up here. Okay, so you've got pre-processing, all of that needs to get done. And we have those 60 first images that go into a single batch, and then we'll have 343 batches, as you can see here. So now we've got our first 10 batches going through. And then if we get this, you should start to see little green bars. Yep, there you go. That it will indicate that the GPU is starting to run, and it's giving you a sense of the GPU compute that's being used. And so we're going to go ahead and give it a break. I'll give you about 10 minutes. So we'll come back at 10 minutes past the hour, give or take. And in the meantime, this will just run and you'll be able to see the full results will be complete when you get done. And then we'll get back to it and we'll talk a little bit about transfer learning and the approaches to using transfer learning with Dask and PyTorch. So enjoy your break, and I will come back in 10 minutes. So then the next thing I want to talk a little bit about is how you might approach a actual transfer learning or general like learning job with Dask. So the inference is, I mean, that sort of classification task or similar sort of thing is oftentimes the really repetitive and high resource sort of utilizing task that we need to do when it comes to deep learning models. We don't need to retrain our models that often, but we might need to classify, some inputs or images or whatnot every single day for, a continued production model. But when we're doing a training job, there's an element that we often run into, probably, at least I've certainly run into this, where we have more data that we could use for training that could be beneficial to the performance of the model than we can actually make use of. And so the memory or compute constraints get in the way of us actually producing the best model possible. And so some of the stuff that we're going to talk about here is going to be, sort of strategies that you might find useful in making sure that your transfer learning or your model training tasks are not constrained unnecessarily simply by resources. And as I said earlier, this is the sort of thing where you need a lot of resources for just a bit, and then you don't need them again for a while. And you don't want to have, built out infrastructure or added a ton of high, expense resources that are going to create a ton of overhead that you don't need all the time. And so that's why we think that the Saturn Cloud approach is the right way to go. So with that, we're gonna stick with our Stanford dogs data set. We're gonna stick with ResNet 50 as our starting point, and we're just gonna use this transfer learning approach to make the model a little bit better at identifying dogs specifically. So we'll do a pre-processing of our data, same thing that we've been doing before. We're going to use the new library that I'm going to talk to you a little bit about called Dask PyTorch DDP, which we built specifically for this kind of use case. And there's also a blog post on our website that goes into a lot more detail about exactly how that library works and about how Dask distributed works. But first off, we've done this a few times now, so I'm going to make you do it a little bit more hands-on. We're going to get the cluster connected because every notebook that you open needs to be connected back to the Saturn cluster so that it knows where our workers are. So here you'll see there's just a couple of fill-in elements that I'm going to ask you to go ahead and do that will make sure that you're really, really familiar with how to do the connection to your cluster. And so we'll set a timer for just a minute to give you a time to do that. All right, I think we're probably there. So, okay, so you could easily open up a little ellipsis and see for yourself, but here we are. Cluster is ready. We've got the sizes and the workers and the threads that we expected, all set. So then we're going to do this thing again where we're going to make sure to assign our device to be a GPU device so that we know that we're making all of our computations and doing the heavy lifting work here on our GPU. And so then we're going to do some pre-processing. So let me explain a little bit about the Dask PyTorch DDP library so that you can use it with confidence and not feel like there's any confusion about what this really is. As you'll see there's a link to our code base and to where the documentation on GitHub lives. So feel free to go check that out, read up on it. And, it's an open source project and we're very proud to have this sort of thing be completely transparent and open to contributions. If you find a gap in what we've built or an addition that you think would be super valuable, we would love to see it and we would love for you to submit PRs or issues. So one of the tools that we built in, which is sort of a necessity, the mother of invention sort of situation, is a Dask PyTorch related dataset class for PyTorch specifically called S3 image folder, because we wanted to be able to load images directly from S3 without having to try to find room on our Jupyter instance to save them to local memory. 20,000 plus images, that just isn't the sort of thing that we wanted to. We don't want to have to set up a Jupyter instance so big that it can house all of that in addition to everything else that we might be doing. So this S3 image folder creates a pointer to our S3 location that can then be, that means that the data on those images can be processed later on in a lazy way when we actually want to call the computation to happen. So we're importing from Dask PyTorch DDP our results, data, and dispatch modules. And then we're also going to get the subset random sampler from regular old PyTorch, which we're going to use a little bit later to do our train test split. Training evaluation split, deep learning lingo. So we're going to pre-process our data. This is not going to be very unusual or particularly unique. What we are using is this S3 image folder that I just mentioned. And once again, this is out of the data module from Dask PyTorch DDP. We're indicating what S3 bucket we're using, what the full prefix for our file path is, what transformations we want to apply, and then anon equals true just tells us that it's a public S3 bucket. We're not going to be feeding credentials. If you do have credentials, you can just leave this out or call it false. Either way will work. So this function, and I need to make sure that I run these things so that we actually have access to them later when we need them. So go ahead and run those. So that just sets us up for creating the transformed images that we need and queuing up the transformations that we want to see so that our images will be ready at the time when we want to actually use them as our training sample or our evaluation sample. So that brings us to our train test split. So we're going to identify what percent, and this function I've written up just as a convenient use case for what we're doing here. So we want to set up the percent of our sample that we want to use for training. We actually pass in this data object that comes out of pre-pro batches. So that is the S3 image folder class object. And then we give it the size of batches that we want to be using. And so we're actually not going to call this yet. We're going to call this in notebook number 6. But these two are the functions that really form the foundation of the job that we're going to do next. So I want to make sure that we're very clear about exactly how we're setting up the data objects that we're dealing with. So once we get done with this, we will have data loader objects. So it's PyTorch data loader objects, one for the training sample and one for evaluation sample. And we're going to use them both in our training. So we can go ahead and run that. And that is setting us up. So everything that we're going to do in notebook number 6 is the actual model work. And so we've got our images and our data all the way that we want them. So we're ready to move on. So you can go ahead and click the notebook number 6 link. And now we're going to, because we just did all of that in a different notebook, I wanted to make sure that things are spread out so that we're not overwhelming you with a ton of like a wall of code in a single notebook. But we have to run it in this particular Jupyter notebook just so that everything is ready. So go ahead and just hit that run for setup number 2 and it will do everything that we just did in notebook number 5. No need to do it all over again. Let's make sure that we've got our client up, and we've got the size of cluster we expected and all of that good stuff. It is just always, in my opinion, a nice handy thing to be able to just double check and make sure that things look the way that we expect it to. Because if for some reason something, if you're using spot instances, for example, and something gets taken back or something like that happens, or some error occurs, this will show it up for you, and it's nice to have that information available. So I'm not going to go into a ton of detail about the way that we're training this model, just to give you the sort of overarching view of how I'm approaching this. Our job here in this particular notebook is not to make the best model available. Our object is to create a workflow that makes sense and seems straightforward that you can then use as sort of a baseline template to go out into your working environment, into your business use cases, and we make this adapted to your needs. So I'm going to use very simple, sorry about that. Cross entropy loss for our last function. I'm going to use SGD for our optimizer, and then I'm going to use a plateauing learning rate scheduler, just because that happened to be what I found worked nicely for this particular data set. But there's no special rules as far as what kind of PyTorch training tools you can use in this. Anything pretty much that is available in the PyTorch library should work for what we're doing. So we're going to have our training and evaluation tasks, and then we are going to run batches of 100 for this case. So we're going to have batches of 100 in our training sample and batches of 100 in our evaluation sample. So there are a few things, however, that for your regular day-to-day use of PyTorch will be a little different, or be, in some way not the standard thing that you would use in a local, single node approach. One thing is the part of the Dask PyTorch DDP library called the Dask results handler. And so what this really is a class that has a few important methods for allowing us to retrieve and save the results of each iteration of our model training, so that we can see the changes in accuracy and loss in every iteration across every worker that we're using. So when we're dealing with this kind of training on a cluster, we have multiple workers running at the same time. And then, as I'm going to explain a little bit later, in the backwards step, they are collaborating on the results that they come up with. But we want to be able to see every worker's performance at every iteration and really keep a close eye on that. So the Dask results handler is a thing that we built in order to make that possible. And you'll see a little bit more about how it all works in a moment. Make sure that I'm running the chunks as we go. So go ahead and run this one. So we have initialized our Dask results handler class. And we're also, I'm not going to have you run these chunks right here because we're actually going to run them later in a big function, but we're going to collect the worker rank. So this is giving us a unique identifier for each worker, just a number, 0 through 2 in this case. And it will just tell us which worker we're dealing with in any given moment. And as you remember, I told you way back at the beginning about how you submit tasks to a worker in the class, in the cluster. You can specify which worker to give it to. You don't have to, but you can. And we are going to in this case, because we want to make sure that for our training forward steps, every worker gets one and only one training task. We don't want to accidentally have one worker trying to do 2 training paths at the same time. That wouldn't work at all. So we need to know which worker we're dealing with. And it's also helpful in the results retrieval process. In the end, we want to make sure we know what worker 0 was doing versus what worker 2 was doing at any given time. We're also going to pass our model to the GPU resources. You're very familiar with this by now. This shouldn't be anything interesting really about this. But so we've also, we're making sure that we give it to a particular device that that is assigned. And then that way our models will be, they're training on the GPUs moving in the forward, on the forward steps. And so we need to make sure that the model knows that it's supposed to be training on GPUs. So then the DDP wrapper, I'm going to talk about this a little more in just a moment because it is a little bit complicated. But the concept is this distributed data parallel framework, which is a part of the PyTorch library. We're going to wrap the model in the DDP so that PyTorch and our workers, all organized, know that what they're doing is training on a parallel multi-worker environment. So single machine parallelized, multi-thread on a single machine is something that's not as complicated and not as difficult when you're dealing with PyTorch. It's not nothing, but it's slightly easier. But when we're dealing with different machines altogether and trying to make sure that those machines can communicate back to the master node in order to not just move forward, but also return back the gradients so that we can continue producing improvements in our model, this distributed data parallel framework is more or less the method for that communication to occur so that cross-machine communication can happen, and therefore our model can and continue to improve. So the PyTorch documentation, and if you've read the blog post that we posted about this specific concept of training and transfer learning with PyTorch and Dask, I've written basically the same sort of notes here that I did in that post, but it basically is trying to instruct us that we're talking about a deep learning workflow. We're parallelizing the applications of this. We are going to be splitting our inputs, which means our batches of images are being chunked and handed off to the workers, while our model, our baseline model, ResNet 50, is not being manipulated at all. It's just being passed to each worker, and they're each going to train moving forward on slightly different batches of images within the overall batch of the iteration. So we're going to chunk those up. ResNet 50 is being altered step by step as we train. And then all during the backwards pass, all of these replicas, 1 per worker, so 3 in our case, are summed back into the original module, and then that information passed back out again for continued training to happen. So I mean, and there's some interesting graphs about exactly how that communication works, because there's a lot of ways that those workers can be assigned to communicate. But in this case, we're doing forward, back, relearn, keep going kind of approaches. So I like to think about it as sort of, a bunch of people all working on a puzzle. They each have a section of the puzzle and they're trying to make progress on it. But once in a while, everyone gets together and talks about their progress, learns from each other's approaches, and that, finds out where they might have been wrong and so on. And then they go back out to continue working and to continue improving and they're all starting from a little bit further ahead because they've all collaborated. That metaphor may not work for you at all, but this kind of helps me to think about how this all works. So we are really ready to go ahead and start training now. It's that simple, actually. So we are creating one big honking function here. I'm going to talk through it a little bit, and then I'm going to leave you to do a little fill in the blanks. And they're concepts that we've discussed, stuff that we've already gone through, so it hopefully won't be too crazy or difficult to manage. There's a couple of functions here that we're going to load in from PyTorch. All of this is PyTorch stuff. None of it is Dask specific. We're just using the stuff that PyTorch already has available. And so in this transfer learning process, what we're actually doing is just running one iteration over the model, right? We're taking our worker. We need to know which one it is. We're going to do the stuff that gets our model all ready to go and make sure that it understands that it's supposed to be working on GPU. We're doing a few steps here involving the stochastic gradient descent and making sure that we know which scheduler we're using, that good stuff. And then our basic learning rate is going to be our world size, which is 3 workers, times the base learning rate that we've assigned, and it'll be 0.01 here. So you'll see that our base learning rate is 0.03. And then we grab our data. We've already got this pre-processing function. Remember, we developed that in number 5, sorry. And then we're going to do our train test split. We also did that in number 5. And then we'll start iterating. So each epoch we've got developed here, we'll go through train, and then we will submit our results on this class, this Dask results object class, remember. So the submissions are actually being fed to that class object that we already initialized. So we'll drop the learning rate and the loss and the number correct and all of these other valuable tidbits that we'll want to know when we are evaluating the model's performance overall. And then every so often, every 100 steps, we're going to checkpoint the model object. Just save one just in case, you never know when the power goes out or something crazy happens. So we want to make sure that we have that available. So we also then have an evaluation step where we will just put the model in evaluation mode, run basically the same sort of stuff over again, and we'll drop those results as well. So we have evaluation sample results that we can compare to our training sample results. And that's it. So we are setting up this function. We are mapping it across all of the stuff that we're doing, although we're going to be doing all of that mapping inside a Dask PyTorch DDP function. I keep doing that. But we're going to get to that in a second. So first now, we've talked a little bit about what this function is. I want to give you a few minutes to go ahead and review that, fill in the blanks. Once again, you've got the ellipsis here with the answers at the end if this is getting a little too confusing, or hit us up in Slack if you have questions that you would like some help with as we go. But I'm going to give you 5 minutes, and then we'll go ahead and move on to seeing how the results actually look. So I'm going to hope that everyone has been able to fill in the elements of this run transfer learning function. As I said, it's a big honking thing. It's got all of the steps of your whole training process in it, but we're going to dump it on each worker once, and we're just going to let it do its thing. So I'm going to go ahead and run that function now just to define it so that it's ready for us to use in a minute. And so then we can just do kind of the easy part, right? We're going to define a few parameters. We're only going to do 2 epochs here because we don't have all day. But if you wanted to actually do this for a broader training task, you might use more workers and you would probably use more epochs. We got our batch size. We already knew what that was because we designed that up above. We're setting in 0.8 training test sample split. And then our base learning rate, we're starting with 0.01, which, as we just mentioned, will be at 0.03 because we're dealing with the scaling up of multiple workers. So go ahead and set that. There's a few little functions that are needed for random bits of this that I don't want to, cause you consternation having to deal with all of that. But we're also going to assign number of workers, which was rightly pointed out that we didn't do in notebook number 5, but is actually referenced. So This is where we're actually assigning it. Sorry, but I missed that. But since we don't evaluate it in number 5, it doesn't really come up until here. So we'll go ahead and set that, get that run. And so we, this is just getting our baseline stuff figured out. And then
where does number of workers come from in particular? Like 64 is not the number of threads. It's not the number of machines. Like why 64? What is?
Yeah, it's, I essentially picked a big number until it looked like I was saturating the GPU. And so the num workers in this case is only used for the data loader, which is primarily doing IO. And so it's just a question of how much, like how fast we can do the IO, how fast we can do the IO and prefetch while the main process is doing the training.
Yeah, the biggest thing that we've really found for this particular task is that the loading the images out of S3 can be the slowest part. And so that was one of the reasons we built that whole, extra infrastructure around loading the data, is because we don't want that to be slowing down the rest of the process. But yeah, this is one of those things where pick a number, test it out, and then later we could tune this, especially if we were building this model for a production use case and not just sort of a demo. We would take a look closer at exactly how that works.
Is this num workers passed to the num workers argument for PyTorch data loader, right?
Yes, exactly.
Yeah.
And so that's total number of workers for the data loader. It's not per node or per.
Yeah. So right now the way that we in when we call dispatch.run, what's going to happen is that there's going to be one training task per GPU in your cluster. So that num workers, it's confusing because there's like Dask workers and then there's like data loader workers, but we've got 3 GPUs. We're going to be running 3 training processes. Each of those training processes is going to be using a data loader, which is running 64 workers.
Okay.
If we rewrote the data loader in a different way, then probably num workers could be lower. But right now it's just because like every worker is just loading an image and then doing a transform. And so that's actually very, very light. And so we have a very large num workers so that we can make sure that when we need to grab more images, it's already been prefetched.
So just to reiterate one thing that I mentioned a little bit earlier, we're not using .map in this case, even though we have a whole bunch of batches of images and we're doing the thing. But we're using .submit because really we want one job per GPU for this training process. And so we're using .submit and we are assigning specifically which worker we're going to use. So with that, we can go ahead and run this next chunk and you're going to notice something. It just creates our futures and it runs, in ridiculously fast. And you're thinking, wait, what? Did something happen? Did I miss something? Did something go wrong? No, it's actually already starting to run now, but we are going to, and we're going to be able to see that in our dashboard links here, but it's not going to hold up our Jupyter instance while it's doing that, just because of the way that this has been written. So what you can do in order to make sure that your Dask results handler object is retrieving and processing the results as it happens, is you can run this chunk down here under retrieve results, and this will hold your Jupyter notebook up because it's sitting there waiting for the results to come in. And when it gets those results, it's saving them out to a folder that you will start to see momentarily in your notebook over here. But let's look at the dashboard in the meantime. So you'll see over here, if we refresh, we have dispatch with DDP, which is the name of the function that we've actually just sent. And there's 3, 1 per worker, and it's doing nothing. It's sitting there, not processing anything in the CPU at all. It's like it's here, it exists, but it is not running on on the CPU. It's running on the GPU, which is what we want. You'll notice our workshop results have started to occur. We've got our workers, and we're starting to see data being dropped out. If we actually look at one of these, you'll see it's producing the results one at a time as we go for each iteration. So let's look at our GPU utilization. Whoa, okay, we're doing it. This is what you want to see. This is how you know your GPU is really doing the heavy lifting and you're not actually just like running it all on the CPU. This is vastly different, as you remember, from the image classification task where we were using both in some content, but this we're really making the most of our GPU resources, which is really awesome. So as you can see, we're starting to get tons of results over here, and that's great. So if we sat down and wait for this, the tests that I've run took 12 to 14 minutes to get this all done. 2 epochs for all the workers, everything got through, and that's nice. But we may not want to sit here and wait all day for that to see some of the results. And I think looking at the results of all the training is actually really neat. So let's let this run and do its thing. We're not going to mess with the cluster. We're not going to interrupt any of that. But let's click the Notebook 7 one. And then I want to give you a chance to just see what it really looks like when you get the results out and you get to look at the difference in performance between 1 worker, 4 workers, 7 workers, or 10. So we've given you a little file here, a little zipped file that is actually the results. It looks just like workshop results here, but under a different name. And if you run this chunk, it'll unzip it for you. And so we've got our stats stuff here. So now if you look at this, see parallel, different versions of the parallel, and then a single node version. So you don't need to mess with anything in there. It's just going to sit there. I've got a function here that we wrote for you that parses the JSON. You don't need to worry about any of that. If you're really excited about parsing JSON, feel free to knock yourself out. But then we're going to process some of the results that we've got in. So we've got the 4 worker, the 10 worker, the 7 worker, and the single node. And we'll just run that real quick. Let it get through all of the JSON that it's going to run. Okay, great. So now I'm using the Plot9 library, and if you're not familiar with that, it's one of the best things that happened to Python visualizations since forever. And then we get something like that. So we can see the iterations, and then these are the kind of epoch breaks, because I've ran this on 5 epochs rather than 2. And then you can see the difference in the learning curve between these. And this is the correct predictions averaged across the workers per batch, which is a batch of 100, of course. So this is what we get. And if we want to see the loss, we can look at it similarly. And these are the training samples. So granted, this is going to be a little bit skewed, but check that out. And you'll see that we're still seeing noise and levels way up into like the 600 iteration stage for a single worker. Whereas you could probably safely call it a day with 7 workers or 10 workers way back here. So you're saving yourself quite a bit of time in terms of the runtime, and your learning is improved all the way back at the beginning. So that, I think, is really exciting piece to keep in mind. So we've got an evaluation sample. We can look at something similar. And then we can do that here too, loss. And that's just, I think, something kind of cool. You can also, if you're interested, use a few other little graphs that I've made available for you if you want to play around with them. But you can also just look at the results here, and that's neat, I think. I like to be able to look at this sort of thing and to evaluate exactly what's going on. We can go back and look at we've got a checkpoint of our model. That means we've gotten through at least 100 iterations, and we've still got our workers spitting out data for us. And that's just, nice. This is a tool, as I said, the results handler is a tool from the Dask DDP or Dask PyTorch DDP library. So it is not a PyTorch native specific thing, but something that we find really handy to have available. And basically that is the amount of what we wanted to cover with you guys today. I would love to answer other questions that you might have. Obviously, you've been asking some questions already in Slack or in other elements here. I noticed John asked a question about how dispatch.run works, and that's one of the elements that we wrote in Dask PyTorch DDP. It wraps up the submit function inside it, and it contains a few other important details. So basically, it defines what worker are you on, checks that checks out like what number that is, and passes that to the .submit. There's other stuff in it, and you can read the whole code base on GitHub, but just for your reference, I think Hugo probably has made that answer already on Slack for you too. But yeah, if you have other questions, please let us know. If you don't want to sit around and wait for these results to come in and mess with them, you're welcome to just stop it, and then we can you can just turn off your cluster if you want to. We've given you credits, so hopefully this will cover all of the experimentation and messing around that you want to try to do today. But yeah, we're really grateful that you decided to join us, and that this has been hopefully valuable. And we hope that you will take some time, mess around in the Saturn platform, see how it can work for your particular use cases, and yeah, get back to us if you have questions or feedback or things that we could improve on. We would love to hear it. But anyway, thank you so much for giving us your afternoon for this, and we will hopefully talk to you very soon.